So let's remind ourselves what we discussed about rotations in the last class. So we discussed that in, for example, in simple spatial rotations, x vector goes to r times x, and demanding that the length of the vector be the same under rotations imposed upon us the constraint that the rotation matrix has to be an orthogonal matrix. R transpose R has to be equal to 1. And of course, this gives us two classes of matrices, one whose determinant is +1 and one whose determinant is -1. And rotation is defined as those set of matrices that have determinant +1. Determinant -1 corresponds to space inversion. Now, just like a translation operator changes the state vector that or any other vector in the Hilbert space of the system by psi goes to some t times psi, a rotation R induces on the Hilbert space of physical states a unitary transformation. This is what all symmetry operators do. And specifically, we are interested in studying those systems that have rotational invariance. Okay, because understanding the action of rotation in systems that have rotational invariance would lead us to a solution that is usually much more simple to understand, just like it happened in the hydrogen atom problem. So even though we study rotations in a general sense, at the back of our mind, we want to apply it to systems that have rotational invariance. Okay, so all the state vectors transform by some kind of a unitary operator corresponding to a rotation R in the physical space. So this unitary operator we call U of R. So it is important to distinguish between R and U of R. R is a rotation matrix that acts on the vectors in the physical XYZ space, or x1, x2, x3, x4, x5, whatever dimensions that you want. But U of R is a unitary operator that acts on the Hilbert space of the physical states. Okay. Now notice that these two are two different objects. That is the first thing that you have to understand. Okay, if I'm living in three spatial dimensions, the dimensions of the R matrix is always 3 by 3. But the dimension of U of R is not fixed because it depends on the dimension of my Hilbert space. If I'm looking at a two-dimensional Hilbert space, U of R is obviously a 2 by 2 matrix. If I'm looking at an n-dimensional Hilbert space, U of R is obviously an n by n matrix. So the dimension of U of R and dimension of R can be completely different. All I'm claiming is that a rotation R in the physical space induces a corresponding unitary transformation U of R. Okay, it is our exercise to find out what this U of R is, and that will be the majority of the first part of our understanding of rotation. So we want to understand what this U of R is. Okay, now just like in translations, you can also equivalently understand the action of rotation on the Hilbert space by claiming that all the operators change by U dagger O U R, right? So just like the usual prescription in quantum mechanics. And we also defined a class of operators called vector operators. Now, if you have any operator, this O prime would be very different from O, obviously, right? But you have a specific class of operators called vector operators. What are vector operators? Well, just like in normal spatial XYZ spatial directions, if you have a vector, under a rotation, the components of a vector mix. So a vector operator in quantum mechanics is defined equivalently. You claim that the new vector operator that you get by evaluating this product U dagger V I U R basically mixes the components of this vector operator. Okay, so to give you a very specific example, suppose if I'm looking at, let us say, the momentum operator, then what I'm claiming is that U dagger R Pi U of R is simply Rij Pj. Okay, which means if let us say I fix I equal to 1, I want to understand how Px transforms under this rotation. All I'm doing is U dagger R Px U of R is equal to R. So no, let me not use X. Let me use 1 because it's easier to add and subtract this way. R1j Pj. This is equal to R11 P1 plus R12 P2 plus R13 P3. Okay, Just like a rotation mixes the components of a vector, a rotation also mixes the components of a vector operator. We will understand a little bit more about what this is in terms of commutation relations today. Okay, that is the first point. Okay, so what is our job? We'll copy paste exactly what we did for translations, except that in this case we have to carry through indices and things like that. So we will first define the concept of an infinitesimal rotation by a very, very small angle. And then we will correspondingly write down this u of r, just like we wrote down t of epsilon, which is I minus, square root, I write this down. So we wrote t of epsilon as 1 minus I epsilon over h bar times p. Similarly, we will write down u of r for an infinitesimal rotation. And then we will figure out what the generators are. In the case of translation, the generators was simply the momentum operator, but we need to figure out what the generators of the rotation are. And this is a slightly non-trivial problem. So let's get started. So let me talk about infinitesimal rotations. So there'll be a lot of indices involved. If at any point you don't follow what I'm writing, please stop me and ask. Okay. Also, please be on mute. Okay. So what is an infinitesimal rotation? An infinitesimal rotation R is some 1 plus some omega. Okay, this is what I would say. Now I should be a little more careful because R is a matrix, right? Now, so let us try to understand this equation. It simply says that to leading order, I don't do anything. So it is just 1 or identity matrix I, plus I do a very, very small rotation that corresponds to some number omega. So omega is an infinitesimal parameter. Okay, just like the epsilon that we used in the previous section. Okay, but again, R is a matrix, and a matrix has indices, a row index and a column index. So if I write it as an index equation, I would write Rij equals delta Ij plus some omega Ij. Okay, so to be very, very explicit, let us take an example of 2 by 2. It's a very trivial example. There is only one rotation possible in this plane. So this R matrix can be written as the first matrix is the unit matrix in 2 dimensions. This is 1, 0, 0, 1 plus some omega matrix, omega 1, 2, omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2. Okay, this is the most general matrix that I can write down with the understanding that all these omega parameters are small. Now here itself, there must be a side question that arises in your mind. Why do we have 4 different parameters? We only have one rotation in a plane. And we will understand that the imposition of orthogonality of these transformations restricts the possible omegas that we can choose. Specifically, we know that rotations are those matrices that satisfy the property R transpose R equals unit matrix. So let us impose that on this infinitesimal rotations. Okay, remember that when I'm imposing a condition on infinitesimal rotations, and if I'm working to order omega, I should be consistent and work to only order omega. I should neglect everything that is order omega square and things like that. So what happens if we put in this condition? Let me take the simplified form of rotation matrix and plug in this condition. So R transpose is 1 plus omega transpose. R is 1 plus omega, and this has to be equal to 1. Everything here is to be understood as a matrix, right? So when I write 1, that is a unit matrix. So what is this? This is 1 plus omega transpose times 1 plus omega equals 1. Okay. So if I expand this out, I get 1 plus omega transpose plus omega plus something of order omega square. Omega transpose omega is of order omega square because it goes as omega 1 square, omega 1, omega 1, 2, and things like that. They are all of order omega square. And I'm going to neglect that because I'm only working to order omega. And this is equal to 1. So if I'm sticking to infinitesimal rotations and I'm sticking with the first order in infinitesimal parameter omega, then I have the condition that omega transpose the matrix of these infinitesimal rotations plus omega equal to 0. What does this mean? This means the transpose of the omega matrix is minus of the omega matrix itself. If the transpose of a matrix is the same as the matrix itself, we call this as a symmetric matrix. If the transpose of a matrix is minus of the matrix itself, then that matrix is called an antisymmetric matrix. So the omega is an antisymmetric object. Okay. In other words, omega ji equals minus omega ij. An immediate consequence of an antisymmetric matrix is that it does not have any diagonal elements, because diagonal elements have j equal to I, and if a number should be the minus of the same number, that number has to be necessarily 0. Okay. So then we'll move on to the 2 by 2 example. In this case, I can write R as 1, 0, 0, 1 plus the diagonal elements should be 0. So let me put 0 here. And since I have only one parameter omega 1, 2, I'll call this as some omega 1, 2. But omega 2, 1 is not fixed because it is antisymmetric. So this has to be minus omega 1, 2. Okay. So in 2 dimensions, my rotation matrix takes the very simple form 1 minus omega, or 1 omega minus omega 1. Okay. Where I just simply relabeled omega 1, 2 as omega. This is the simplest antisymmetric matrix I can write down in 1 dimensions. Of course, I can generalize this to write it in 3 dimensions and so on and so forth. So the imposition of orthogonality immediately means that my omega matrix has to be antisymmetric. So this I'm sure you have seen before, but let us now come back to the problem of trying to understand what the induced operator on the Hilbert spaces. So what is this U of R? So let me write down what can be the form of U of R for an infinitesimal rotation. Okay, so let's be very clear on the question that we are asking. We are asking that in the physical space, I am doing a very, very, very small rotation by an angle 10 to the minus 40 degrees, right? So correspondingly, if I'm investigating a quantum mechanical system, what is the corresponding operator that is acting on the state vectors of the Hilbert space of the quantum mechanical system? What is U of R for this particular infinitesimal rotation? So just like we wrote down what is T of epsilon, let us try to understand what is U of omega. What is U of omega? Again, to leading order, it has to be just I or 1, whatever it is. And it has to be, so let me actually write down the T of epsilon first, so you can make a connection. T of epsilon we wrote as I minus I epsilon over H bar times some generator G. Again, the form is always identity matrix plus I times some infinitesimal parameter epsilon or something times a generator G. So let's write down U of omega. U of omega should be I. Okay. Now plus or minus doesn't make any difference. So just to prove that point, I will write plus here. I. Okay. Again, I will choose H bar, but I will actually choose 2 H bar here for reasons that will become clear towards the end of this lecture. Okay. If not this lecture, at least the next lecture. I over 2 H bar. Now, what are my infinitesimal parameters? My infinitesimal parameters are omega. How many omegas are there? Well, that depends on the dimension of transformation. So if I'm sticking with 2 by 2, then there is only 1 omega. But if I'm doing rotations in 3 by 3, there is 3 possible omegas, right? There can be a omega in the xy plane, yz plane, xz plane. So in general, I should write this as omega ij jij. Okay. Now these omegas are, so let me make this clear. This is the infinitesimal rotation angles or parameters. And these are the generators of rotation. Okay. Now, before I move on, let me actually clear up something about the indices here. Notice that omega ij jij should not be read in the same way you read rij. When I write rij, I wrote it somewhere here. Where did I write it? Here. Rij, when I write it as delta ij plus omega ij, what I mean is ij here refers to the row and column index, right? R11 means the 1 element of the R matrix. Jij should not be read the exact same way. Okay, so the I and j here refer to something else. We will understand what is something else by working the transformation of jij completely in the tutorial. So to be more specific, the I and j index here should not be understood as the I and j here in the R, but rather they should be understood as the way we understand the I index in the P here. Okay, it is actually a vectorial index. It doesn't refer to the row 1 column. So what does this mean? This means that, for example, in 2 by 2 in two spatial dimensions, there is only one J matrix. What is that J matrix? Omega 1 2 J 1 2, right? So in 2 dimensions, U of omega, I can only write this down as I plus I over 2h bar omega 1 2 J 1 2. Okay. So in 3 dimensions, and this J12 is a matrix, some 2 by 2 matrix. We had to figure out what this 2 by 2 matrix is. In 3 dimensions, if my physical space in which I'm doing the rotation is 3 dimensions, the corresponding operator induced in the Hilbert space is I plus I over 2h bar. Now there is 3 possible omegas, so correspondingly there will be 3 possible j's. I can write this as omega 1 2 J12 plus omega 23 J23 plus omega 13 J13. Okay. And so on and so forth. In 4 dimensions, there'll be more generators. So how many generators? Well, I told you that rotations form a group called SON, and SON has n times n minus 1 over 2 independent components. So in 2 dimensions, n is 2, so this is just 1. In 3 dimensions, n is 3, so this is 3 times 3 minus 1 over 2, which is 3. In 4 dimensions, it is 4 times 4 minus 1 over 2, which is equal to 6, and so on and so forth. Okay. So the first lesson that we have to understand, which is different in the case of rotations as opposed to translation, is that in the case of rotations, I should write this infinitesimal transformation as omega ij times jij. But remember that omega as an object is antisymmetric in the indices I and j. So we have to understand that this jij should also be something that is antisymmetric in the indices I and j. Because if jij is completely symmetric in the indices I and j, then the product omega ij times jij would simply be equal to 0. Remember, the product of an antisymmetric times a symmetric object is always equal to 0, right? So if there is a symmetric component of jij, that symmetric component would always vanish in the definition of U of omega. So we simply take jij to also be completely antisymmetric in the indices I and j. So jij is also antisymmetric in the indices ij. This means that jij equals minus jji. Okay. So what does this mean? So in the case of 3 dimensions, viewing this as simply an object with 2 indices I and j, I can also have j12, j21, j22, j11, j33, j32, so on and so forth. But there is only 3 that remains because If J is an antisymmetric object, J11, J22, J33, all the diagonal components are by definition equal to 0. And again, J12 is minus J21, J23 is minus J32, and J13 is minus J31, which means there is only in total 3 independent objects. And these 3 independent objects we call either J12, J23, or J13, or simply J1, J2, J3 in 3 dimensions. In fact, we will adopt the simpler notation of J1, J2, J3 towards the end, but first I want to keep it completely general. Okay. So this is the first point. This is how I will write down the infinitesimal operator induced by an infinitesimal rotation in the physical space x1, x2, x3, x4, x5 space. Okay. So we have to understand the properties of these G matrices, and we have to understand what the properties of J matrices are. Remember that the dimension of R has nothing to do with the dimension of J. The dimension of J is determined by the dimension of the Hilbert space that we are looking at. That is the first point. So that is why I and J and the J do not refer to row and column. It simply refers to independent matrices. So J12 is a matrix, J23 is a different matrix, J31 is a different matrix, and these matrices would also have rows and columns, but we have to understand them separately. Okay. So we will do a tutorial problem in which we will understand what this Jij object is. We will actually figure out that this is actually a tensorial object. It transforms like a tensor. Okay. Now, before we move on to tensors, we want to stick with vectors, and we want to understand what this infinitesimal transformation means for the transformation of a vector. So remember that we defined the notion of a vector operator as one in which the transformed vector u dagger r vi u r is simply equivalent to mixing up the components of a vector. Okay. So today we will simply look at this equation and use the fact that I'm doing an infinitesimal transformation u. Okay. So infinitesimal transformation u, infinitesimal transformation r. So what does this equation mean for an infinitesimal transformation? So evaluate this for an infinitesimal rotation. Okay, that is what we'll be doing now. Okay, so before we move on, if there is any questions, please ask.
Sir?
Yes.
Sir, you told that these are independent, omega and J are independent matrices.
Yes.
So then, but the way you wrote the equations that omega 12 J12 for 2 dimension, then omega 12 J12 plus omega 23, these are the this would be the independent components of the matrix, na? Omega, right? So this, since omega would be antisymmetric, then omega 12, omega 23, these aren't these the elements that are making it the independent elements of that antisymmetric matrix?
The independent elements of the antisymmetric matrix. Okay, so I don't understand the question completely, but let me try to clear up the confusion if there is one. So let us stick with 3 dimensions, for example, right? So I claim that this u of omega that I wrote down is I plus I over 2 h bar omega ij jij, right? Now in 3 dimensions, I can write, so in 3 dimensions, I know that there is only 3 omegas, independent of quantum mechanics. Just by looking at the rotation operator, I know that in the case of 3 dimensions, there can be only 3 omegas, right? Because omega is an object that is antisymmetric in the indices I and j. And if I write it down, I will have in 3 dimensions, a omega 1, 2, omega 2, 3, and an omega 1, 3. Those are the 3 independent omegas in 3 dimensions. Is this okay?
So that's what I'm referring to, that since these are elements of the omega matrix, omega ij.
Correct.
So but you said that omega in this u operator is a matrix by itself.
No. So omegas are still parameters. The j's are matrices. So, okay, so the way you understand this is as follows. See, the U is a matrix, agreed?
Yes.
Okay. Now, let us actually work this out. So, in two dimensions, there is only one omega. Yes?
Yes.
Okay. So, two dimensions. What is this U of omega? The U of omega I can write as I plus I over 2h bar. Let us call this omega 12 J12. Correct? Okay.
Hmm.
Yes or no?
Yes.
Okay. Now, let us make a very important point. In two dimensions, omega is not a matrix. It is just a number because there is only one omega.
Okay.
Yes?
Yes.
But this U still has to be a matrix. So the way you understand this is by saying that this can be understood in two dimensions as I plus I over 2h bar, some number or some parameter times some matrix. Okay? And this matrix is J12. Now, this can be a little confusing because you're absolutely right. Omega ij, when I write omega ij, the I and j here refer to the row one column of the omega matrix that I wrote down here. Okay. But all I'm saying is that the I and j on the j are not the row one column of the j matrix. It is some other index. Some other index that is simply summed over. Okay, what this index is, we will come to later. We'll actually understand that Jij and the I and j are actually vectorial indices, and j is actually a second rank tensor. Okay, so let me move on and talk about three dimensions. In three dimensions, U of omega takes the form I plus I over 2h bar. Now, I know that independently of quantum mechanics, in three dimensions, there is three omega parameters because rotations are always orthogonal transformations. So there is only three omega matrices that are three omega parameters that are possible. I will choose these three omega parameters as omega 1, 2, 2, 3, and 1, 3, which means the sum. Because in this sum, everything is summed over omega ij, jij. I should write in three dimensions as omega 1, 2, j12 because the I and j is repeated summed over plus omega 1, 3, j13 plus omega 2, 3, j23. Now, how should I understand this? The omega 1, 2 itself is some number. Remember that the omega is a matrix, but omega 1, 2 is a particular number in that matrix. So in the case of 2 by 2, omega 1, 2 is the 1/2 number of the matrix R. Does this make sense?
Sir, then uh, do I can I consider it like omega 1 2 would be the, if it is two dimension, then it is like the xy plane rotation of the xy plane
Yes,
would be
absolutely.
about z.
You can understand omegas purely by looking at the XYZ axis. You
Yeah,
don't need to go into any quantum mechanics.
and then again for three dimension it would be like 1 2 would be xy rotation of the xy plane, that is about the z. Then yz, which is 2 3, which is about x.
And about Z, which is,
Around, and yeah, and the same.
yeah. So the reason we are doing it in the more general fashion is that, it can also completely extend to arbitrary dimensions. So 4 dimensions, 5 dimensions, in which it is not very straightforward to imagine, you can still define the rotation operator in exactly the same way. Okay. Another reason I'm doing it this way, even though I can simply just give you what JI-JJ commutation relation is and start with this, which is what most quantum mechanics books do, is that for those of you who want to study a little more about relativistic quantum mechanics and so on and so forth, if you do a course on field theory, this is exactly the language you would employ, except that in that case, you would actually talk about not SON, but SO31. Okay, Lorentz transformations are SO31. So you would actually be talking about a J mu nu. In relativistic theories, the Jij would be replaced by a J mu nu. Oh, sorry. So this is not showing up. So let me stop share and reshare. So these would be the generators of space-time rotations or Lorentz transformations. Okay, so this language generalizes very readily to beyond single particle non-relativistic quantum mechanics also. Anyway, so in this equation, please understand the omegas as parameters of transformation and the j's as matrices or generators. Okay, that is all I want to say. At the end of it all, that is what this means. Omegas are numbers, j's are matrices. Simple. Okay, so I will.
So,
Yes.
so if omega is a number, then what's the point of saying that product of symmetric matrix and antisymmetric will be zero? Matlab, how do we then how will we consider J as antisymmetric matrix?
So again, an object can be symmetric or antisymmetric without having a matrix representation, right? So if you look at omega in the case of space rotations in this way, you can think of an omega matrix, which is this, right? So it's tempting to think of omega itself as a matrix, and there is nothing wrong with that. But suppose I can also define an object like, say, A, I, J, K, right? Is there a matrix form for this A, I, J, K? This is an object with three indices, right? Now, this object with three indices can have very many properties. It could be symmetric in the indices I and J, or it could be symmetric in the indices J and K, or it could be antisymmetric in the indices I and K. So I'm inviting you to think of this as abstract object with some indices. You can think of them as matrices, but you should also be comfortable in thinking of them as objects with some indices. So viewed that way, omega is an object with two indices, and excuse me, it is antisymmetric in the two indices, which means if I multiply it by another object, two index object, Jij, then in the product, the only thing that survives is the completely antisymmetric objects component. So I'll explain what this means. In this case, it's not clear. So let us take three dimensions again as an example. Okay, so omega ij, jij, right? So let us say that jij. So in three dimensions, I can go from 1 to 3 and j can go from 1 to 3. So in principle, jij can have j11, j12, j13, j21, j22, j23, and j31, j32, j33, all these different numbers inside, right? Whether it's a matrix, you can write it as a matrix form or simply leave it as jij, it's up to you. Now, I know that omega is antisymmetric in I and j, which means omega 1, 2, I know to be equal to minus omega 2, 1. So suppose if I don't impose any restrictions on jij and I simply calculate what this product is, let me go ahead and calculate this. So I can have things like omega 1, 1 is 0. So j11 doesn't matter because j11 never enters this product. So I can forget about j11, I can forget about j22, I can forget about j33. Because omega 11 is 0, omega 11 times j11 is obviously equal to 0, no matter what j11 is. So here I will have omega 12 j12 plus omega 21 j21, omega 13 j13 plus omega 31 j31 plus omega 23 j23 plus omega 32 j32. Agreed? Yes, these are the elements that I will have in this summation. But I know that omega 12 is minus omega 21. So for example, if I expand this out, I can write this as omega 12 times j12 minus j21. And so on and so forth. Does this make sense? Excuse me.
Yes, sir.
Okay. So which means that if J is a symmetric matrix, if J21 is the same as J12, this is obviously equal to 0. Yes?
Yes, sir.
So which means that Jij, if I decompose this Jij as two objects, an object that is symmetric in I and J and an object that is antisymmetric in I and J, In this expansion, omega I, ij, jij, all the A components would vanish. Only the B components would survive. Okay? Because
sir.
all the omega, because omega is already antisymmetric, all the A components would obviously be equal to 0. All the symmetric components of J would obviously vanish, and so we might as well take J to be a completely antisymmetric object in the two indices I and J.
Okay.
So regardless of whether I choose to look upon omega as a matrix or look upon omega as an object that is antisymmetric in the two indices I and J, I can get the exact same form for the infinitesimal rotation U of omega. Make sense?
Yes, sir.
Any other questions by anybody else? Okay. So our job is to look at this infinitesimal rotation and look at this transformation for a vector and understand what this transformation rule implies for the case for infinitesimal rotation. So let us plug everything. So U is, for infinitesimal rotation, U of omega is 1 plus I over 2h bar omega ij jij. Excuse me. Okay. Now, omegas are parameters of rotation. So omegas are by definition real parameters. And without any loss of generality, I can also take J to be real. Because I want the I times J to be a Hermitian matrix anyway. So U dagger VI UR, this equation can be written as, I'll use I dagger would be a minus I over 2h bar. Dagger is complex conjugation. Complex conjugation doesn't affect omega ij and jij. Followed by a transpose. Transpose does affect omega ij and jij. Transpose simply means I'm interchanging the two indices I and j. But if I interchange the two indices I and j, omega gets a minus sign and j also gets a minus sign. So the product does not get any minus sign. So I can still write this as omega ij, or rather I will write this as omega kl jkl times vi times ur, which is I plus I over 2h bar omega kl jkl. That is the left hand side. The right hand side for an infinitesimal rotation, as we discussed, is delta ij plus omega ij times vi. Sorry, vj. So let me change the indices. Oops, excuse me. Let me change the indices slightly. So I'll write this as ILBL. The L index is summed over. Okay. So now I have to expand both sides of this equation. And we will have to expand both sides of this equation. And this will tell us something about a relation between the components of a vector operator and the generators of rotation J. Okay, I don't want to do it now. I will do it in the next class because I also want to explain the physics behind this equation. Okay, so today we will stop here. All I'm trying to do is understand how vectors behave under rotations. To understand how vectors behave under rotations, I want to understand if there is a relation between the vector operators and the generators of rotation J. In fact, if you look at your previous semester's notes, you already know the answer to this question because we worked out the commutation relation between any vector and the orbital angular momentum operator L. Okay, we will derive the exact same thing, but from slightly more general grounds. And then we will also generalize this to angular momenta that is beyond just orbital angular momentum. I'll explain what this means in the next lecture. Okay, so we'll stop here and please understand that even though the notations can be a little confusing, ultimately what we are doing is writing the induced operator on the Hilbert space excuse me, as 1 plus I times a small parameter times a matrix, and that matrix is a generator of that particular transformation, in this case rotation. And then we want to understand how various objects behave under rotations. We'll be studying two different objects. The object that we will study in the lecture is a vector operator. A vector operator simply mixes the rotation simply mixes the components of the vector operator in the Hilbert space. And we'll also understand in the tutorial a tensor object. A tensor object is something whose two indices get mixed in exactly the same way as if it was two vector indices. Okay, we will make this connection more precise in the tutorial problem on Monday. But on the next lecture, which is Thursday, we will press on with this problem and we'll try to understand um, what this equation basically is telling us. What is the connection between Vi and JKL? Okay, this is the ultimate goal that we want to understand. And then we will move on and generalize this to the commutation relations between the J's themselves. Okay, and that will tell us something very interesting and something that you probably already know. Okay, so for today we will stop here. And then if you have any questions, please ask.